All right. I see folks are rolling in, and it is now 2 o'clock. So, welcome everyone to today's Third Coast Water seminar. My name is Tyler Steven. I'm the technical program manager at Current, and we are the leading organization behind this series. So today's Third Coast Water seminar will be brought to you by Dr. Jacob Jones out of North Carolina State University. And he'll be giving a talk on phosphorus sorbents and their role in phosphorus sustainability. So before I turn it over to him and you guys can hear all about his expertise and what he's got going on, wanted to provide a little bit of background about the Third Coast Water Seminar Series, Current as an organization, and initiative that we are anchoring called Great Lakes Renew. So first and foremost, I wanted to thank the subcommittee of Current's R&D partners that put together and select and recommend speakers for this series. We have one of those members on the call today who will be introducing Dr. Jones. They are really kind of guiding the direction of this series all around this central point of elevating speakers who are doing work related to transforming waste into wealth. So thinking about resource recovery and harmful contaminant destruction. Yeah, so the Third Coast Water Seminar Series, we restarted it earlier this year. This is the fourth installation of this series this year. And it's created by originally by Current. So Current is a nonprofit water innovation hub based in Chicago. We were founded in 2016, so we're approaching our 10-year anniversary next year. Our central mission is kind of around three core principles. So the first is catalyzing the circular blue economy. We also want to accelerate water innovation by convening and connecting various stakeholders, be it researchers, industry stakeholders, entrepreneurs, and communities. And then we also want to solve pressing water challenges while driving economic opportunity and protecting environmental and public health while safeguarding our nation's most critical um, national security asset, which is fresh water. So Current as an organization, as I mentioned, is the anchoring organization behind the NSF-backed and funded regional innovation engine called Great Lakes Renew. Renew standing for the recovery of energy, nutrients, critical elements, and water. This is a multi-state regional effort across 6 states in the Great Lakes region, focused on those core principles of recovering energy, nutrients, elements, and water. And we fund projects from research and development to workforce development to translation of novel technologies into the commercial state. So we are spurring the circular economy transition, supporting the invention and commercialization of selective separation technologies, as well as hoping to attract and retain water-intensive industries in the Great Lakes region. So I mentioned research and development is one of those key priority areas that we are supporting through this Engines program. These are just a list of some of the things that we are funding and supporting. And this is kind of guiding where we're going with this Third Coast Water Seminar Series. We want to elevate work and people doing innovative research into these areas. So from PFAS detection to critical mineral extraction to nutrient recovery and the likes. If you would like to learn more about Current or the Great Lakes Renew Initiative, we encourage everyone to follow us on socials. You can scan that QR code and that'll lead you to our website. But without further ado, I will pass it off to Dr. Vinayak Dravid, who will be introducing today's speaker. Vinayak?
Inspiring colleague. I will spare him long introduction, but give you some highlights. Jacob is the Kobe Steel Distinguished Professor of Material Science and Engineering at NC State. And he also directs the NSF STEP Center, is the largest such program that NSF offers. And so in a way, it's the nation's flagship efforts in phosphorus sustainability. He also leads a research triangle nanotechnology network that runs the NNCI in that region. And so he obviously doesn't know how to say no. And that's one of the traits that I like about Jacob. In terms of his research, he uses in situ X-ray scattering and advanced characterization operando method to look at dynamics of inorganic materials from functional ceramics earlier part to more recently nanomaterials for phosphorus recovery. And through STEPS program, he now coordinates more than 150 researchers over 30 disciplines, truly a tour de force in sense of convergence research. And so he manages 30 disciplines as a part of this STEP program. And I've always mentioned this to him earlier, that it comes across very aspirational, yet nice and very polite. And so I figured he must have some Midwestern connection, only to find recently that he spent almost 26 years in Indiana, not too far from the Renu Reach. And so we want to welcome back Jacob to Renu region, and I look forward to hearing from you. Thank you.
Thank you, Vinayak. That was very kind. I'm going to share my screen, Tyler. Just let me know if there's any technical difficulties.
Yep. You're all good.
Great. So I want to thank the organizers for the invitation to share some of our interests and work here in this particular forum. I think there's a lot of synergy between our NSF Center focused on phosphorus sustainability and the NSF Renew engine. And one topic at the intersection of that is phosphorus in the Great Lakes and its role in eutrophication of water quality. And that is why I've chosen to highlight, out of all the work that STEPS undertakes, highlight the topic of phosphorus sorbents today. And of course, before we start, I want to acknowledge that our understanding of the challenges and needs in this space has been the result of a center-wide collaboration over many years. And our thoughts and contributions are those of my colleagues and are gratefully acknowledged. So I've chosen to break this presentation into 3 chapters. In the first one, we'll motivate the need by exploring why we care about phosphorus and phosphorus sustainability. In the second chapter, I'll introduce the NSF STEPS Center as a convergence research center. And in chapter 3, we'll introduce phosphorus sorbents, highlighting both some of the work in STEPS as well as successes elsewhere in the field. So chapter 1, why we care about phosphorus and phosphorus sustainability. In the most simplest way, we care about phosphorus because it's required for all living things to grow. In fact, phosphorus is an essential nutrient for animals, plants, and microbes. It facilitates their cell development. It's a key component of molecules that store energy like ATP, that process information like DNA, and that form cell membranes. It's so essential that the U.S. National Institutes of Health, or NIH, lists the recommended daily allowance of phosphorus as 700 milligrams for adults and 1,250 milligrams for children aged 9 to 18. This larger RDA for children reflects their need to use phosphorus to grow. And in our case as humans, we store most of that phosphorus in our bones and teeth, and phosphorus makes up about 1 to 1.4% of our fat-free mass. Phosphorus is similarly critical to growing healthy plants and crops, including those in agriculture and those used to produce food. The need for phosphorus to grow food was elevated to the national level when in 1938, the US President Franklin D. Roosevelt talked about the importance of phosphorus to economic security of our nation. His speech was informed by tests at the time, one of which is shown here in the photograph at the right with vegetables, that the application of phosphate demonstrated an ability to encourage the growth of crops and the yield of plants. He went on to say that a high level of productivity can only be maintained when phosphorus is returned to the soil, and that it must be made largely, if not entirely, in the form of fertilizers, which are derived from phosphate rock. And before moving on to discuss the subsequent growth in phosphate rock mining, it's important to note the timing of this event, which was before the U.S. entered World War II. And after the war between the 1940s and 60s, you all may know something about a population boom, significant enough to be called a baby boom. And it was the growth of mined phosphate rock and its subsequent use in fertilizers that helped feed that growing population at the time. And you can see the effect of this continued application of phosphorus fertilizers, its effect on the productivity of the U.S. agricultural system in a number of different ways. You could track, for example, the yields in agriculture over time. This is the amount of product produced per area, like acre. And take corn, for example, one of my favorites, being from Indiana, hopefully one of your favorites. A photograph at the left very clearly shows the role of phosphorus fertilization in growth and subsequent yield of corn. And the data on the right shows the yield of corn over many decades in time, the yield being a measure of the crops grown per unit area and its productivity indicator. And while the yields were relatively flat prior to the 1940s, the yields of crops increased steadily since then due to both the intentional application of more phosphorus fertilizers, as well as the parallel developments in new crop varieties, which also used more and more phosphorus. And as a result of this continued application, we've grown dependent upon phosphorus fertilizers to maintain our level of food production, with the annual global mass of mined phosphorus quoted here at the top from about 2 million metric tons per year to around 20 million metric tons per year, or a tenfold increase. In part because of our dependence on phosphorus fertilizers to grow food, to feed Americans and to feed the world. Only a few weeks ago, so this is recent news, the USGS elevated the mineral phosphate to the list of critical minerals. And at the right over here, you can see I've outlined in a red box the identification of phosphate. Now it's now on the same list as elements like rare earths for application in things like magnets for energy and defense applications. We're still working as a center to understand the consequences and the implications of adding phosphate to this list, but it's going to clearly play out in some areas shown at the bottom, things like federal policy, permitting processes for mining and beneficiation, and scenario planning, for example. Once phosphorus is mined, it's critical to understand how we use it in the global food system to start to appreciate some of the challenges and some of the opportunities. And on this slide, we show what we call a mass flow diagram. And engineers like me like to do mass balances to make sure they obey certain laws, like conservation of mass, for example. You can't destroy mass or create mass. And this figure is one of the balances shown graphically, or rather, as you'll see, it's an imbalance to be quite precise. On the top left, you can see phosphate rock's primary use in fertilizers. And the width of the arrows here scales with the mass of elemental phosphorus flowing into these different pieces. And the first thing to highlight on a diagram like this is the mass imbalance problem in agriculture. A lot goes into the system. You can see a couple of very big arrows, but only a little comes out. This is a major internal loss that accounts for the mass imbalance, and it's an inefficiency in crop systems that leaves a lot of phosphorus in soils. It's sometimes diffuse and often not available to crops because of its chemical form, but it's there. A second feature is the loss of phosphorus to surface waters, the loss through agricultural waste and human waste, to be more specific, which causes downstream problems like eutrophication. This agricultural waste comes from sources like drainage ditches, and animal and field runoff. And the photograph here in the upper right is a famous experiment from the 1970s from a lake in Canada, where they were able to curtain the lake into two sections and dose it on both sides with nitrogen and organic carbon. But on one side, they additionally dosed it with phosphorus. And it's a striking photo of a key historical experiment that demonstrates the role of phosphorus on inland eutrophication and harmful algal blooms. Finally, in this diagram, it's useful to illustrate our role as humans in this process. Only 20% of the phosphorus that comes into the global food system actually enters the human diet. The rest, a lot of it, is wasted. Another important point here is that although humans make up a small portion of this diagram, it's our behaviors that create the entire upstream demand, one of the many social science aspects that must be considered here. Now, with all that said, I want to go back to the original number, 18 million metric tons or 20 million metric tons. That's a lot of mass. And it's so much, it's even difficult to imagine how much mass that is. And so scale matters. And maybe that's a phrase that's a theme in STEPS because we say it a lot. We scale across many different dimensions. So let's try to understand how much mass that actually is. One way to imagine it is equivalent to something we know, which could be an aircraft carrier, something heavy. So a new unit of mass I'd propose for the purposes of illustration is the unit of an aircraft carrier. Now, 20 million metric tons is equivalent to elemental phosphorus in weights equal to 200 aircraft carriers, fully loaded. Okay? Now, there's only 40 aircraft carriers in the world, 11 of which are in the US. So this is a tremendous amount of mass that's entering the global food system. And we're using that mass annually and only recovering a small fraction of it in food, and most of it's lost. Now, as a material scientist, I also like to compare these numbers to other elements that we're familiar with. Aluminum, for example, every time you drink a soda or fly on an airplane, or lithium, every time you recharge your rechargeable battery. So with aluminum, for example, aluminum sourced from bauxite, that's the mineral that's mined, and the numbers are on the same order of magnitude as phosphorus and phosphate rock. But we're much better stewards of aluminum than we are with phosphorus. Lithium is also pretty important these days because of its use in batteries, and we're good stewards of lithium as well, even though there's 3 orders of magnitude less of it that we mine. So scale matters at the microscopic levels as well. Now, here represented as concentrations in the units of parts per million, or ppm. And starting at the bottom, we can see on this schematic the levels of phosphorus in the natural background are around 0.03 parts per million, or in a different unit, 30 parts per billion. That's a really small concentration. Now, the EPA recommended levels to prevent eutrophication are slightly above this, around the 0.1 ppm level. And then all of the other examples on this slide are larger than that. Wastewaters at 5, swine lagoons around 200, soils with a medium around 800, and urine at about 1,000 parts per million. So in total, that's 5 orders of magnitude different in concentration. And it emphasizes the needs to keep these high concentration materials away from surface waters to protect surface waters. Now, we can connect these global masses with the small concentrations that we see locally in environmental matrices, and we can do it geographically. Now, on this slide, we highlight some STEPS work that has integrated several large databases to map both the inputs of phosphorus to the environment and the losses of phosphorus around the US. And some useful conclusions from this scientific work are shared at the right, but I don't want to spend too much time on it here in this particular presentation. But maybe worth highlighting is this third and last bullet, which talks about the need for targeted nutrient management that's specific to the ecologically heterogeneous areas of the country and of the world. Now, Renew's engine, their region of interest, I think is very important here. We can see the Midwest shows both heavy inputs as well as heavy losses, things that you are no doubt very familiar with. And finally, we can see the impacts of some of these losses to the various environments. Now, usually I just share the example on the right, which is in the Gulf region. But today I'm sharing an additional example, which is of high relevance to you. In the Gulf example, we know that the dead zone is one of the world's largest and is driven by nutrient pollution, which includes phosphorus. And this obviously has significant economic consequences. And for today's talk here at Renew, I added the distribution of total phosphorus represented as a single point in time, where phosphorus, the concentration of phosphorus being colored. So areas that are red would be in higher levels of phosphorus. And Lake Erie has the most red color, as you've shown here, but there are many other hotspots associated with excess phosphorus. So this is a challenge that's all around the Great Lakes region. And I would be remiss if I didn't acknowledge another byproduct from the processing of phosphate rock. This may be less relevant to the Great Lakes region, but it's still here in our backyard. And that is in the production of phosphorus-based fertilizers, we produce a byproduct called phosphogypsum. And this byproduct is sufficiently radioactive that it cannot be used in other products, and it cannot be disposed of in landfills. So this byproduct is stored indefinitely in large mounds or stacks, often topped with acidic water containing phosphorus and other chemicals. You can see an example of the stack here in this left photograph, located in close proximity to Tampa Bay in Florida. Now, these stacks pose both immediate and long-term challenges to both humans and the environment. As one example is shown here, a breach in the phosphogypsum stack in April of 2021 created a state of emergency in Florida. The concern was that an initial leak, small leak in one of the retaining walls would steadily increase, causing an uncontrollable flood of acidic water through the communities. And to remedy the immediate threat, the acidic water containing high concentrations of phosphorus was pumped into Tampa Bay over the course of days. And while this eliminated the immediate threat at hand, it placed a significant load of phosphorus into Tampa Bay, and the phosphogypsum stacks remain. Now, folks familiar with these aspects often ask the question, well, could plant-based diets be the solution? And at face value, this seems like a really good idea. On the left here, we see the relative amounts of phosphorus required to yield certain food products. Meat, especially red meat, represented here by bovine meat, is the largest amount. It requires a substantial amount of phosphorus to yield this food product because of the amount of phosphorus required year after year to grow food to feed the animals. So naturally, if you and your doctor, and I emphasize you and your doctor, decide that a plant-based diet is appropriate, you'll reduce what I've called here your upstream phosphorus footprint quite substantially. You will require less phosphorus to grow the food you eat. But if you shift your diet toward consuming more plant-based foods, you'll consume more phosphorus in those foods because of the nature of the food itself, meaning you'll excrete it downstream, increasing your downstream phosphorus footprint. So the result is overall reducing the impacts, but it's shifting some of the burden from the fields to the treatment plants. Now, all of this to say, this is a very complex problem with no single solution. So nevertheless, there are some obvious things that we know. We know we need to reevaluate and reduce phosphorus application. In the US especially, there's already sufficient quantities out there. We know we need to reduce runoff from both point and non-point sources. This includes wastewater treatment facilities and edge of farm. And we know we need to be able to remove it from surface waters and soils, the former to prevent eutrophication and harmful algal blooms. But it's not an easy problem. To fully address it, we'll have to work across an incredibly large number of disciplines that Vinayak mentioned earlier and across length scales. If you consider the size of phosphorus at the smallest scale and the earth at the biggest scale, we say this problem spans 17 orders of magnitude in length scale. At the smallest scale, we need chemists, physicists, materials researchers to understand phosphates, materials for capture and recovery. At the length scales at which humans interact with technology, we need crop, soil, animal, we need environmental scientists and engineers. And at regional and global scales, we need to understand factors in sociology, public policy, and economics, which drive some of this. Now, these types of disciplines needed to tackle this challenge, they certainly include the physical science and engineering, but they extend across the life sciences, the social sciences, and the economic sciences. And so we pitched this problem as being ripe for what NSF captured in one of their 10 big ideas, which was growing convergence research. Now, for those of you who may not be familiar with this phrase convergence research, I share this slide with the NSF definition, which is twofold. First, that the research undertaken must be driven by a specific and compelling problem. And second, that it must be a problem that requires deep integration across disciplines. And I would add here, deep engagement across stakeholder groups, something you're also familiar with in the Renew program. And that brings us to Chapter 2, the NSF STEPS Center. And the photograph I show in the back is the home of our physical headquarters of STEPS here at North Carolina State University. STEPS was funded in 2021 as an NSF Science and Technology Center, or STC. It's a collaboration across 11 organizations shown at the bottom and also identified on the map. And in the words of one of our reviewers, it's a convergence research center with phosphorus sustainability as the vehicle. Each year, STEPS includes about 190 participants. Some of those are summer participants. And so our regular academic year participation is around 120 to 150. And finally, there are 5 photographs over here at the left of ecosystems. And they show our so-called triple bottom line sites. These are physical locations I'll introduce later in which STEPS deeply studies local challenges like stakeholders, local soils, local waters, local policy, etc. Now, STEP's mission is shown here, and that is to develop and implement convergence research on phosphorus sustainability across those disciplines, those scales, those sectors, and those communities that first generates new knowledge. We're a science and technology center. And the second innovates new phosphorus sustainability solutions. And the third that trains scholars who are equipped to address complex societal challenges. And here we define scholars in the NSF STEP Center as undergraduate and graduate students and postdocs. And we're proud to report that in the first 4 years, we've been able to have 76 of these scholars graduated or completed our programs, which includes 30 graduate students and 11 postdocs. Now, when we created STEPS as an original proposal, we engaged experts from the field of science, of team science, and integration and implementation science. And we pulled together best practices in order to create research structures and processes that facilitated convergence research. Some of those structures are physical objects or locations that connect researchers to real-world problems. We call these boundary objects. It brings about a way of connecting researchers from diverse disciplines that are otherwise difficult to connect. One of those objects is the phosphorus flow diagram I showed before. Every researcher in STEPS can tell you where their work connects to the P-flow diagram, and therefore the P-flow diagram connects us. Another important boundary object for STEPS is what we call these triple bottom line scenario sites. These are specific physical locations that allow students and researchers to connect their work with specific systems. These sites have well-defined inputs and outputs. They have well-defined system constraints, existing data, and stakeholder narratives that we can use to study the triple bottom line factors to sustainable solutions. And they become important objects for student immersion and center integration. We published a paper not long ago here at the right that describes the TBL sites and how we use them. And then in our renewal process, we expanded from the 3 you see here to include 2 additional ones, one of which is in the Corn Belt there in the Midwest. Now, STEPS also pioneers what we call convergence informatics. I'm not going to focus on this a lot today, which involves the use of machine learning and AI to help solve problems. Examples drawn schematically here at the bottom include predicting groundwater composition in undersampled areas, in optimizing costly synthesis and characterization of nanomaterials, and then design of phosphorus sorbents such as peptides. And just a couple months ago, we also had the opportunity to play a key leadership role in the scientific community around promoting convergence research. Through supplemental funding from the STC program at NSF, we organized and hosted a workshop on the topic of both theory and practice in convergence research centers. This involved a substantial amount of pre and post work before and after the workshop, and we'll soon share in open access format a compendium of the best practices identified through this collaborative exercise. So STEPS further advances a compelling phosphorus sustainability vision. And that is to facilitate a 25% reduction in our human dependence on mined phosphates and a 25% reduction in losses of point and non-point sources of phosphorus to soils and water resources within 25 years, leading to enhanced resilience of food systems and reduced environmental damage. Now, this is an aspirational vision that inspires the team. It helps direct resources, and it seeks to inspire the entire U.S. research community. Here at the beginning is the word facilitate. This isn't an entirely STEPS problem, but we want to build a community that helps advance this vision. And it's aligned with subsequently published goals from the USDA, shown here at the left, and the global yet European leaning report called Our Phosphorus Future. Working together with stakeholders in 2022, we produced a roadmap toward U.S. phosphorus sustainability, which identifies 9 so-called impact opportunities shown here at the right. And I emphasize that this is not a roadmap for STEPS. It's a roadmap for research across the U.S. on phosphorus. And these opportunities promote things like, here starting at the bottom, optimizing use, reclaiming waste, recovering valued products, reducing waste, and enhancing monitoring. And it also makes suggestions on how to grow markets and accelerate solutions, something important for phosphorus sorbents, as we'll share later, as well as the need to increase awareness of phosphorus sustainability beyond agriculture and into society at large. Now, one way in which we've been able to increase awareness, this top so-called transformative opportunity, is to claim the 15th week of every year in celebration of our favorite element on the periodic table, the 15th element. So we've been doing this now for a couple of years and accomplishing more each year. We're introducing you here to Phosphorus Week. This past year, one of our new successes was to be able to get 4 governors of states in which STEPS has a presence to proclaim the 15th week of the year as Phosphorus Week. This includes North Carolina, Wisconsin, Illinois, and Arkansas. And I think 2 of these are of interest to Renew, at least 2. Each of these proclamations state the relevance of phosphorus to their state. Let me take Illinois as one example. Whereas it's essential for life and crop growth in Illinois, whereas Illinois' ag industry provides the state with $51 billion annually in economic value, where the specific amount of fertilizer and phosphorus fertilizer used in the state is stated, and where we need to protect the environment, people, and water recreation industry, which is around $3.2 billion. And so there's a reference to our initiative, which is collaborative in the state. And as we move forward, we hope that with your help, the community around Renew, we could amplify this further in 2026. So mark your calendars right now, April 6th through the 10th, the 15th week of the year, in celebration of the 15th element on the periodic table. And think about how you can help amplify our messages around understanding phosphorus sustainability and some of the challenges, and maybe coordinate outreach activities or presentations in order to promote awareness at all levels. All right, so finally, Chapter 3, Phosphorus Sorbents. And the image in the back here is a chemical map from a transmission electron microscope showing the relative locations of nitrogen and phosphorus in a microbe from a wastewater treatment plant. So in a way, this is both a beautiful image and a very icky one at the same time. Now, sorbents are used in a lot of applications. In your kitchen, you sorb water, soap, you sorb grease. Maybe that's through absorption or adsorption. These are 2 terms important to physical scientists, but not to the general population. So let's just say they're sorbed. So sorbents are also used for gases, with one application being CO2 capture. And for manipulating or capturing phosphorus from environments, it's useful to think about different environmental matrices in 2 dimensions. The first is vertical on this plot. High flow rates or large volumes at the top, and low flow rates or small volumes at the bottom. The second is horizontal, high phosphorus concentrations at the right and low phosphorus concentrations at the left. And I want to call these quadrants that arise as a result of this representation as the Westerhoff quadrants, because our team member and co-deputy director, Paul Westerhoff, was the first to suggest presenting it this way. So of obvious interest to STEPS are things in the upper right quadrant. Think of large masses of phosphorus used in agriculture each year and the large concentrations in soils and plants, clearly of relevance to addressing phosphorus sustainability. Some matrices in the lower right include things like swine lagoons, again, very common in North Carolina, and human and animal urine, also of great interest to STEPS because they're bounded and they can be processed readily. Now, in the upper left, we have large volume or flow combined with low phosphorus concentrations. Now, this includes surface waters like in South Florida, where we've done a lot of work, and also in the Great Lakes region. And I'm putting up here just a reminder of what concentration levels we're talking about and how that varies significantly from some of the higher concentration matrices. All right. Just to finish it out, this last quadrant in the lower left is interesting, but not necessarily interesting to STEPS as the others are. It may capture things like pet waste, for example. Now, while all 3 of these quadrants are of interest to STEPS, today's presentation on phosphorus sorbents is really focused here in the upper left. We can learn a lot from these other quadrants, but we need to focus our attention today in this specific presentation. And also, although I've been using the word phosphorus pretty loosely up to now, as we enter some more scientific slides, I want to specify that the sorbents of interest here are for capturing orthophosphate, or PO4, which is the form that drives eutrophication and harmful algal blooms. But we have chemists and material scientists on the team who study and work with many other phosphorus forms, including those beyond those shown on the slide here. And I think it's important to state some metrics of success, both to manage our own expectations as well as strive for ambitious achievements when possible. Now, urgently, as we know from the Great Lakes, as one of many examples, we need to be able to capture orthophosphate from surface waters to mitigate eutrophication. Ambitiously, there's a version of this where you could engineer or design sorbents so that the phosphorus can be removed and can be reused in agriculture. But remember, there's a very small amount of phosphorus in surface waters relative to the large amounts that we need in the food system. And finally, there are some important scientific metrics of success, like new knowledge, specifically on how sorbents work and how they can be scaled to larger application spaces. Now, some typical sorbent forms and applications are shared on this slide. The form is typically an aggregate, a powder, or granule, as in the photograph here at the top. And these materials can be engineered or natural organic materials. They can be polymers, gels, metal organic frameworks, or MOFs, and others. One example would be iron oxide would fall into this, or lanthanum carbonate, or aluminum hydroxide, for example. And their deployment is typically achieved in one of two ways. There's direct application here on the right of powders or slurries to surface waters, or there's the inclusion of the sorbent in a porous material for targeted use, such as in streams or inlets to waterways, shown here at the left. And importantly, this one at the left is retrievable or recoverable, whereas the one on the right is not, and typically finds its fate at the bottom of the water body, something to consider. Scientifically, there's a wide variety of ways in which sorbents capture orthophosphates. Some examples of how metal cation-based sorbents, like iron oxide, can capture P are shown here schematically. These top two, this inner and outer sphere complexation, involve strong bonds to a surface-exposed metal cation. The capacity of this mechanism is strongly dependent on the available surface area because it's a surface phenomenon. So sometimes we talk about specific surface area, which happens to be surface area by weight. This bottom example, surface precipitation, can occur when metals leave the sorbent and bind with an orthophosphate from the solution to form an entirely new compound, like iron diffusing out of the sorbent and reacting at the surface to form iron phosphate. And there's some other scientific underpinnings that are shared here at the right, but we'll leave that to the expert for now. There are several commercial materials available. Phoslock is the most widely recognized, as it's been around for a couple of decades. It was invented at CSIRO, which is a research organization out of Australia. Phoslock uses a mineral called bentonite. The bentonite mineral is modified chemically with lanthanum, a rare earth element, and sold as a dry powder or an aggregate, shown here. A photograph of a treated water body is shown at the left relative to an untreated water body here at the right. Now, this material works by capturing phosphorus on its way down the water column as it settles through the column, often thought to be a surface precipitation mechanism, as we introduced on the previous slide. And the product is typically only used once. It's single-use application, so it's relatively expensive. Another new product on the market is called Utrizorb, which comes in several different formulations for specific environments. Here some numbers are given. It's reported that a 50-pound bag can recover a half pound of elemental phosphorus, shifting the concentration in a pond by about 0.05 ppm, just enough maybe to mitigate eutrophication. Now, one fundamental challenge associated with these products is that they're expensive, especially if you use them once, and it makes it difficult to scale them to larger bodies of water. And they do use that rare earth element lanthanum, which, by the way, is also on that critical minerals list I shared earlier. And so some of our earliest work in my own research group contributing to STEPS was to better understand how lanthanum worked so that we might be able to mimic that behavior using other materials that are more economically advantageous. So some of our work on studying lanthanum carbonate early in the process is highlighted on this slide. After immersion in an orthophosphate solutions with synthetic solution that we created in the lab, we analyzed the particles in a transmission electron microscope and used a technique called energy dispersive spectroscopy to do a chemical analysis at very small length scales, very similar to that image that we started out the chapter with. And the microscope images at the left and the chemical maps at the right tell an important story. With increased immersion time from 2 minutes at the top to 6 hours in the middle to 51 hours at the bottom, the solid particles from the solution get smaller. And the phosphorus, which was initially near the surface, eventually becomes more homogeneous throughout the particles. Now, this result suggests that the sorbent's not capturing phosphorus via adsorption, as it is at the beginning, but instead is through dissolution and reprecipitation of a compound. This bottom particle reflects a chemically homogeneous lanthanum phosphate compound. Now, I should mention that we did a lot of other characterization work to prove this, but I think the electron images are the most compelling to share in this particular presentation. Another important thing we did early on was to survey the literature to see if we could make more global conclusions about mechanisms of phosphorus capture by these lanthanum-containing materials. And so we identified 73 reliable reports in literature first, and then compared the amount of phosphorus captured on the vertical axis against the specific surface area on the x-axis. Now, there's no clear trend. Higher surface area doesn't yield better capture. So this suggests that adsorption phenomena is not the mechanism. And instead, when we compare the amount of phosphorus captured across these 73 articles, we notice that it does correlate with the amount of lanthanum that's there. So this is very close to a 1-to-1 ratio of the amount of phosphorus captured to the amount of lanthanum present, which corresponds to forming a lanthanum phosphate-based compound across a large range of different types of initial compositions. So what does this mean? What does it mean that lanthanum is leaving the host material and reacting with the orthophosphates to precipitate this new compound? Well, one implication is the possibility of losing lanthanum to the environment. And so many have wondered about whether it's a problem to use or leave lanthanum, or certain other elements for that matter, of interest to Renew in the environment. And there's a small body of work where folks are trying to answer this question, but there's a lot more unknown than there is known. There's a lack of risk characterization data for lanthanum in the environment, as well as many other materials, and there's no regulatory thresholds for lanthanum concentrations. Now, what these papers do know, and what is common knowledge in the field of phosphate adsorption, is that lanthanum carbonate hydrate is also the active ingredient in a pharmaceutical called phosrenol, which is prescribed to patients with end-stage renal disease to capture phosphorus in the human body. Now, one report has suggested that a human would have to eat 404 kilograms of eel liver from a treated lake to intake the same amount of lanthanum in a daily dose of phosrenol. So high concentration of lanthanum, and you would have to have a large mass. Now, I don't know about you, but scale is important here too. 404 kilograms, that's the weight of 6.5 average weighing human beings. And that is certainly a lot of food. So there's this one opinion out there that any current lanthanum levels are safe. I do not take this opinion, but it is one published in literature that I think I need to tell as part of this story. What we've been doing lately, led by one of my colleagues, Kara Grieger, is to understand relative environmental risks for many different types of metal cations that are used as sorbents. Environmental risk here includes ecotoxicity, bioaccumulation, and persistence. And one of the things that they determined is that while lanthanum-based materials had low to moderate risk, this is in the middle bullet, aluminum and iron-based materials have low to high risk. And meanwhile, metal cations like calcium and magnesium have low risk. But importantly, what they observed is a dearth of information on bioaccumulation, persistence, and chronic ecotoxicity. So we're operating without important information and making decisions on interventions and engineered solutions. And these are certainly areas of needed research for sorbents to be designed and deployed with minimal risk. Now, there's a lot of opportunities to enhance performance of such sorbents if we can understand their relative impacts to the environment. On this graph, I show some results out of my own group by my student Daryl Harry in collaboration with Detlef Knappe. And the y-axis here represents the amount of P captured, and the x-axis is the amount of P in the initial solution of the experiment. Now, if all the P in the experiment can be captured, experimental data would follow this dashed line up here. Now, these data sets are for a variety of inorganic materials. We're not sharing the chemical compounds on this slide, but the two comparative commercial materials are certainly identified. And 3 of these new materials perform much better at higher concentrations than the commercial materials. So the team's using complementary tools like the electron microscope we shared before and X-ray diffraction to understand fundamental absorption mechanisms and conditions of optimized performance. We're also looking at selectivity as to how these materials capture phosphorus in the presence of other anions and how regenerative it can be. Can it be used twice? Can it be used 5 times? Can it be used 50 times? Because that significantly affects the economics at play. We're also looking at ways to deploy the materials for recovery. So some of this involves the use of scaffolds, larger structures that can be retrieved, but that still have sufficient performance. And this allows me a nice segue to highlight some work that comes out of the Midwest at Vinayak Dravid's group at Northwestern. So in 2021, we were excited to read their publication in PNAS, reporting a new phosphorus sorbent material coined as the pearl membrane. The patent for this was just released a few months ago. It's identified there at the bottom. And this is based on a cellulose structure which is abundant, and they have to process to attach magnetic nanoparticles that contain iron oxide. And iron oxide is the functional or active element in this material. But it's on a recoverable scaffold, which makes it very convenient. So the plot at the right shows great selectivity for phosphorus, even in the presence of competing ions. And although I'm not highlighting on the slide, but you can read about it in the paper, their work also shows that this particular solution can be reused more than once. It can be regenerated with good performance at least a few more times. And it's been licensed to and commercialized by Coral Innovations, a startup company that I visited on my recent trip to Northwestern. So I think it's a great example of innovation and technology transition and should be inspiring to many working in this field. Another great example in innovation and tech transfer comes out of the STEPS work funded at NC State. This is through the group of Professor Jan Ginzer, who developed a new sorbent based on a polymer hydrogel. So by mimicking phosphate binding proteins, the material is designed for high selectivity, efficiency, and reusability. It efficiently releases captured inorganic phosphate under mild conditions relative to its competitors, and has been demonstrated to be reused multiple times, making it more economical than other sorbents. This technology is patent pending. Some details are at the bottom, and it received the university's Chancellor's Innovation Fund Award to promote and help with technology translation and commercialization, as being discussed with some companies. And a new version of this technology is also being designed for use in the plant soil microbiome, which would be a different quadrant in that Westerhoff quadrant plot. Now, finally, on this last technical slide, I wanted to highlight a new project that NSF funded through the REDOT program. REDOT stands for Responsible Design, Development, and Deployment of Technologies. And the project focuses on South Florida, TBL site of STEPS, and a location where we've had a center retreat, and we have a lot of collaborations. In South Florida, over a period of decades, this is a beautiful story if you want to read up on how government has collaborated with industry and universities in order to solve a major problem. But over a period of decades, they've been able to substantially reduce the phosphorus leaving South Central Florida and entering into the Everglades Agricultural Area, EAA, and then eventually through something called the Stormwater Treatment Areas, or STAs. And you can see a point source there leaving the STAs and going on down into the subsequent areas of South Florida. So while these STAs average 77% reductions in total P each year, which is a really good value, they're insufficient to reach a key new 2027 requirement of 0.02 ppm. So this project is engaging stakeholders to assess the requirements around implementation of sorbents at key outflows, like in this photograph, based on regulatory constraints, costs, scalability, product assessment, and availability. And we invite your participation in this project and your help by completing the survey piece, which is currently open. So hopefully you can get your phone out real quickly, but I will also share this QR code on the next slide if you don't have time to capture it. So finally, and this is my last slide, some calls to action for the community. Help us promote phosphorus sustainability in the public consciousness by following and amplifying Phosphorus Week, coming up with your own outreach activities to your own regions of interest. Join STEPS through the STEPS Partnership Program. I didn't share this on a slide in this presentation, but you can learn about it on the website. We're partnering with industries, other academic partners, and whatnot. Listen to the Phosphorus podcast. This is a podcast that was envisioned by and still is maintained by our scholars in the center. And there's some really good material for your commutes to and from work, for example. Follow STEPS on LinkedIn. We're very active, and we, in turn, follow Renew, and want to make sure that we're promoting the interest of our respective programs. On the R&D side, I think the call to action is to engineer to recover deployed sorbents and reuse them. There's a lot of chemists, chemical engineers, and material scientists working to understand at the smallest scales how these sorbents work, but then we need to be thinking about how to scale them up. And that's going to involve some collaborations between materials engineers, maybe mechanical engineers, environmental scientists, and agricultural engineers. We need to be building industry academic partnerships to translate and scale technologies. We're doing some of that now in steps. We have some small projects that industry is participating in, but that is a key need, I think, in this entire scientific area. We need to be developing and growing markets around phosphorus recovery and accelerating technology adoption. Like I said, I do not think we can build a case for phosphorus sorbents based on the amount of phosphorus they recover. I think the intent needs to be to remove it from large water bodies. And then take our survey to help the South Florida project understand stakeholder requirements. So with that said, I think we still have about 10 minutes or so for questions. And I just want to thank you again for this opportunity to share our work and hope you learned something new. Thank you.
Awesome. Great presentation, Dr. Jones. It was really great to see everything that's going on. We do have a few questions in our Q&A box, but if anyone else has questions, feel free to drop them in there over the next few minutes. So yeah, we can jump right into it. So first, you brought up several examples of like a lot of the innovations in the space of phosphorus sorbents that are particularly geared towards those environmental applications. I was curious if you could maybe summarize what are the particular criteria that you would say define success for a novel sorbent?
Yeah, what are the criteria for success? I think I dipped my toe in that on one of my slides where I said, what's the metric for success, right? I think that this depends a lot on your application. It depends a lot on your resources. It may depend on policy. It may be unique to different environments. But I think generally speaking, if the goal is to help control phosphorus in large water bodies, I think that cost and reusability absolutely have to be considered. As well as, I spent some focused time on thinking about potential release of these materials into the environment and whether or not there's ecotoxicity things to be thinking about. So, yeah, someone could probably frame this in a way that is sensitive to all of the different application spaces in which you could deploy it. But I would say, some of the main things are the ones I just listed: cost, scalability, deployability, recovery, and potential impacts.
Great, thank you. Wow, lots of questions. Everyone's super engaged. So let me just skim through some of these really quick.
Oh, here's a great question. What happens if nothing is done? If it's business as usual, what's the urgency? So, yeah, well, if nothing is done, we're going to continue putting more phosphorus into the environment, and we're going to have more harmful algal blooms and more negative economic consequences to both recreational facilities as well as fishing, and probably other types of secondary impacts. And you can probably quantify that through some economic calculation process. I've been trying to understand, this is far outside my field, but I've been trying to understand environmental economics. And if we had people that would be able to quantify that for us, I think that would be a great help.
Awesome. There's several questions about like the mechanisms of different how different sorbents work and like the some of the things that may need to be considered in different applications. So I guess like what what are like some of the different like challenge or sorbent selectivity criteria for, say, like an environmental like low concentration water body versus say like a high concentration like a lagoon that you were mentioning? Like could you use lanthanum for both of those applications or does is that really only is that like application specific, I'd say?
I long for the day when we have a lot of different solutions, which we don't have it right now, right? I mean, scientifically, we're evaluating a lot of different solutions, but if you go to a company that works in this space, they have a limited number of things that they can apply.
Hmm.
And I gave some examples of commercial materials earlier. But yeah, I think that again, each situation may be unique, depending on the size of the water body, what's in there from a biological perspective, what the pH is, um, so many factors. And like again, I'll just go back to what I said earlier. I dream of a day when we're able to select from a list of 50 different sorbents which one is ideally suited for that particular environment.
Yeah.
But we just don't have it now. So experimentally in the lab, when we're investigating, a dozen different types of materials, we run controlled experiments. We look at the performance as a function of pH, as a function of concentration, as a function of time, and we're learning a lot about that. But translating that into a portfolio of products is challenging. Transferring that to a single product is challenging, and I commend Vinayak for being able to do that thus far with the pearl membrane.
Great. Great call to action there as well. Um, awesome. And then here's a general one. So, how is STEPS working with institutions to help build capacity towards working on phosphorus related issues?
That's a great question. When STEPS was funded, we didn't propose a robust membership or partnership program because it wasn't required from the solicitation. But as soon as STEPS was announced as a center, people came flocking, wanting to know, how they can work with us. We were just getting the center up and running, so it took us a couple of years to kind of formulate a partnership program. Now it's formalized. It's available on our website. I didn't highlight it in the slides, but it should be readily apparent where it's at on the website. And I think it would be great to sit down and have conversations with folks working in industries. There are a number of different ways that we can work together above and beyond just research itself. So, for example, in making sure that we're training students for the jobs of the future, we'd like to hear from industries on future hiring needs. We'd like to make those matches with folks on our side. One of the things that we're really proud about from the workforce development perspective is being able to train scholars and graduates that can understand big problems and find their unique little contribution to a really complex problem. And so they can do that through participating in our Convergence Research Center. But then when they graduate, they don't have to work on phosphorus sustainability. They could work on other problems. At the beginning of your slides, Tyler, you talked about PFAS, you talked about recovering critical minerals from waters. And I think all of those problems require the type of individual that we're trying to train in the center.
Great. Um,
Oh, can I pull a question up?
yeah, go for it.
So there's one here that says, since 80% of mined phosphorus comes from a single country, Morocco, is there a geopolitical, national, or security angle? So this is a very important question. I want to correct the data, though. I would say that 70% of the world's phosphate rock reserves are located in Morocco. In fact, here in the U.S., we source most of our phosphorus domestically, which is why we've got that phosphogypsum stack problem that I mentioned. And just interesting curiosity is look at your own body and look at your bones. Where do you think that phosphorus came from? Depending on where you grew up and where your food was produced, that phosphorus had to come from somewhere. I'm thinking most of the phosphorus in my bones originated from Florida. So I can connect to that phosphogypsum stack in a very unfortunate way. So since Morocco holds 70% of the world's phosphate rock reserves, is there a geopolitical national security angle? Absolutely. So I think the recognition of phosphate as a critical mineral on the USGS list gives us the ability to have more conversations with government agencies around food security and the need not just to, I think in many people's minds, the need to be able to mine more phosphate, but I would argue the need to recover phosphorus to use it in local environments. I mentioned before that I wouldn't advocate for developing these technologies as a way to source massive amounts of phosphorus for agriculture. It's just not economical, right? But locally, you can reuse it. And I think that we should be thinking about the local microeconomies in this, which touches on another question on regenerative agriculture. But yeah, I think it's an exciting space.
Great. Well, we are just about at time.
I
So
appreciate
I'm,
all these questions. We don't have time to get to them all. I don't know if everyone sees
yeah,
them, but
yeah, a lot of questions.
there's
Yes.
another question here. It's pretty quick, if you don't mind. Are there related STEPS similar organizations in other countries? The answer is no, because STEPS funds research, and there's nothing as large and comprehensive as STEPS in other countries. But there are other platforms, like Europe. Europe has the European Sustainable Phosphorus Platform, which brings people together. very similar to our Sustainable Phosphorus Alliance, which brings people together, which is an extension arm of STEPS. So yeah, thanks for that question as well.
Perfect.
What a fantastic job, Jacob. Sometimes, it's very difficult to define a problem, but you did so beautifully.
If only we could solve the problem so beautifully and so quickly.
One step at a time.
Thank you.
Amazing. Well, thank you again, Dr. Jones. Really great to hear from you. For folks that are on this call and really enjoyed this presentation, we'd love to invite you to our next seminar, which will be occurring on January 7th at 11 a.m. Central Time. It will be virtual. There's the link to sign up for it, or you can go to Current's website and register there. We will be hearing from the Hampton Roads Sanitation District on growing a regional innovation ecosystem. And with that, thank you all for joining us, and we hope to see you at the next one.
Thank you.
Bye.
Great job. Good to see you, Jacob. I'll see you on the other